Every soldier who goes to war accepts one harsh truth. He might be killed. A bullet, a shell, a bomb. These are understandable, tangible enemies. But in the trenches of World War II, another killer lurked, unseen, silent, and merciless. A killer that didn't arrive with an explosion, but with a whisper. It entered the body through a trivial scratch, through a piece of shrapnel that barely broke the skin, through an open fracture, and it began its dirty work. For a German soldier in 1944, a deep wound in his leg, even if it missed vital organs, was often a death sentence. Within a few days, the wound would begin to throb, a fever would spike, chills would rack his body, gangrene would set in, and the only salvation, if any, was a surgeon's saw. Thousands of soldiers who survived the fighting died in hospitals, from what we treat today with a simple course of pills. They died from bacterial infections. But on the other side of the front, something like a miracle was happening. An American soldier with the exact same wound would get a shot, a simple injection of a yellowish fluid, and the next day, the fever would break, the infection would retreat. In a week, he could be ready to return to duty. The Germans couldn't understand how it was possible. They saw the statistics. The Americans were returning their wounded to the line at an incredible rate. It was like magic, but it wasn't magic. It was America's most powerful secret weapon of the Second World War, a weapon that saved more lives than any other. Its name was penicillin, and the story of how America turned a laboratory curiosity into an industrial miracle changed not only the outcome of the war, but our entire world. To understand the scale of this revolution, you have to go back to a world without antibiotics, the world our great-grandparents lived in. In the First World War, nearly as many soldiers died from infections and diseases in hospitals as they did on the battlefield. Any surgery was a life-and-death lottery. Surgeons could remove the bullet, but they were powerless against the microscopic invaders that entered the wound along with dirt, fragments of uniform, and bits of metal. The main enemies were bacteria, staphylococci and streptococci. They caused sepsis, blood poisoning, tetanus, and gas gangrene. The treatments were barbaric by modern standards. Wounds were flushed with antiseptics that killed not only the bacteria, but also healthy tissue, slowing down healing. Surgeons practiced debridement, the radical excision of all damaged and contaminated tissue. If the infection spread, amputation was the only option. The doctors fought, but they were losing. In the 1930s, a glimmer of hope appeared: sulfur drugs. This was the first real magic bullet against bacteria, and Germany was the world leader in their development. Sulfur drugs saved many lives and were actively used by both sides at the beginning of the Second World War. But they had serious drawbacks. They weren't effective against all bacteria and often caused severe side effects. Moreover, bacteria quickly developed resistance to them. Something entirely new was needed, and that something had been gathering dust on a shelf in a London laboratory for nearly a decade. In 1928, the Scottish scientist Alexander Fleming made one of the most famous accidental discoveries in history. Returning from vacation, he noticed that a mold had grown on one of his petri dishes containing a staphylococcus culture. But the interesting part was what was around the mold. The bacteria near it looked as if they had been dissolved. They were dead. Fleming realized that the mold, Penicillium notatum, was producing some substance that killed bacteria. He called it penicillin. Fleming was a brilliant scientist, but not a chemist. He conducted several experiments, confirmed that the mold juice killed many types of dangerous bacteria while being harmless to animal cells. But he was unable to isolate the pure, stable, active ingredient. Penicillin proved to be incredibly temperamental and fragile. It broke down with the slightest change in temperature or acidity. In the end, Fleming published his findings, but the scientific world paid them little attention. The idea of mold juice as medicine seemed unpromising. 10 years later, in 1939, the world stood on the brink of a new war. At Oxford University, two scientists, Australian pathologist Howard Florey and German Jewish refugee biochemist Ernst Chain, were looking for new areas of research. They stumbled upon Fleming's forgotten paper. Sensing that the coming war would bring millions of infected wounds, they decided it was worth another try. Their work was a titanic effort, They turned their lab into a veritable mold factory. They grew it in anything they could get their hands on. Hospital bedpans, milk churns, bathtubs. They developed a complex purification process to obtain a tiny amount of an unstable brown powder. In 1940, they conducted a crucial experiment. They infected 8 mice with a lethal dose of streptococci. 4 of them were injected with penicillin. The next morning, the 4 untreated mice were dead. The ones that received the shot were perfectly healthy. It was a victory. The first human patient to receive penicillin was a London policeman named Albert Alexander in 1941. He had scratched his face on a rose thorn, and the wound became infected. The infection spread throughout his body. He was near death. After the very first injection of penicillin, he began to improve. But the supply of the drug was minuscule. The scientists collected the patient's urine to re-isolate the precious drug from it, but it still wasn't enough. After 5 days, the supply ran out, and the policeman died. This tragedy proved 2 things. Penicillin worked miracles, and it needed to be produced on an industrial scale. But Britain was under bombardment. Its industry was stretched to the limit. And so, in the summer of 1941, Florey and his colleague Norman Heatley took a desperate step. They got on a plane and flew to neutral America. Their mission was secret. To avoid attracting attention, they didn't bring samples of the mold with them. Heatley simply rubbed the spores into the lining of his coat. They arrived in America, in the arsenal of democracy, with a single hope: to convince the US government and industry that mold juice could win the war. And America listened. The project was handed over to the Northern Regional Research Laboratory, NRRL, in Peoria, Illinois. And it was here, in the heart of agricultural America, that the real revolution took place. The Peoria scientists faced 3 gigantic problems. First, the mold needed food. The Oxford team had grown it on a simple nutrient broth, getting a meager yield. A chemist at Peoria, Andrew Moyer, began to experiment. He tried dozens of additives, and one day he added corn steep liquor, a byproduct of corn processing, which was abundant in Peoria, to the broth. The result was stunning. The yield of penicillin increased 10-fold. Then he added milk sugar, lactose, and the yield doubled again. Second problem: a better strain of mold was needed. Fleming's original strain was a weakling. The lab sent out a call across the country asking for mold samples. And one day, a lab assistant named Mary Hunt, who earned the nickname Moldy Mary, brought in a moldy cantaloupe from a local market. The mold from that melon, Penicillium chrysogenum, proved to be hundreds of times more productive than the original strain. Nearly all the penicillin produced in the world is descended from the mold on that very cantaloupe from Peoria. The third and most important problem: the production method. Growing mold in thousands of bottles was inefficient. They needed a way to grow it in huge industrial vats. The solution came from the brewing and chemical industries: deep tank fermentation. The idea was to make the mold grow throughout the entire volume of the liquid, constantly pumping sterile air into the tank. American pharmaceutical giants like Pfizer, Merck, and Squibb already had experience with this technology. The US government brought together 21 private companies. They shared patents and technologies. A race against time began. The goal was to produce enough penicillin for all Allied forces by the time of the Normandy invasion. And they did it. By D-Day, June 6, 1944, American industry had produced 2.3 million doses of penicillin. It was one of the greatest industrial achievements of the war. Now, let's return to the battlefield. An American medic, leaning over a wounded soldier, would first treat the wound with sulfur powder to stop the infection on the spot. Then, at the field hospital, the soldier would get a shot of penicillin, and a miracle would happen. The death rate from bacterial pneumonia in the US Army fell from 18% to less than 1%. The risk of dying from an infected fracture dropped by 95%. Gas gangrene, that scourge of military hospitals, practically disappeared. Doctors were able to perform the most complex surgeries without fear that the patient would die from infection. It changed everything. And the Germans? They knew about penicillin. German scientists were also working on it. But they could never solve the problem of mass production. Fragmented companies, a lack of government support, and constant bombing prevented them from making the industrial leap that America had. For them, penicillin remained a laboratory rarity. Their soldiers continued to die from infections, while the Americans had a drug that saved almost everyone. In that sense, penicillin wasn't forbidden to the Germans. It was unattainable. It was a weapon they could see, but could not copy. After the war, penicillin became available to the entire world, ushering in the age of antibiotics. It has saved hundreds of millions of lives. It has turned deadly diseases into curable ailments. We live in a world built on the legacy of this discovery. The story of penicillin in World War II is not just a story about a drug. It is a story of how, in the face of a global catastrophe, science, government, and industry can unite to achieve the impossible. It is a story about mold from a cantaloupe, about corn steep liquor, about huge steel vats, and about the thousands of nameless scientists and workers who, in the quiet of laboratories and the noise of factories, forged one of the most important tools of victory, a weapon that did not destroy, but saved.